The new section that we're starting today is going to emphasize the relationships between work and energy that we have been studying so far, but we're going to begin to pull together some mathematical tools and some graphical modeling. All skills that you are used to so far in this course, we're just applying them to some new content. To begin, we're going to talk about how we graphically analyze the work that is done on a scenario. Graphs are really important in physics. We use them when we talk about position and velocity and acceleration. We also can use them for force. So I've got two examples on the screen here for you. The one on the left is showing you a constant force that's applied to an object that causes it to move throughout a displacement. So for example, maybe you take an object and you push it with an applied force of 10 newtons for 20 meters. How can we graphically represent that? So I want you to take your pen or your pencil and I want you to sketch a graph showing you a constant force applied to an object that causes it to move through a displacement. I'll give you about 5 seconds. You should have just drawn a nice straight horizontal line across the center of your graph. Because if it is a graph of force versus time and it's a constant force, we need to show a constant line. Notice just things that are going to be different from problems that we have seen in the past. We're still dealing with a measurable vector quantity on the y-axis. Here we're dealing with force. Most of the graphs that we've looked at so far this year, though, have been something versus time, where time has been on the x-axis. And in this particular case, we're actually looking at force versus distance. So just be careful with your units here. So this would be a graph showing you an object that experiences a constant force over a certain distance. And what I want you to consider is, as with most things, the slope of this graph tells us something, and the area of this graph tells us something as well. Now we're going to put a pin in that for a minute, but I want you to just keep that in the back of your head that we don't just graph for no reason. We graph to be able to solve and have some more tools. Take a look at the graph on the right-hand side. Again, this is another graph of force versus distance. But this time we are not going to assume that we're working with a constant force anymore. With all of the work that we've done, we have looked at scenarios where a constant force has been applied. Now that doesn't mean that the object won't be accelerating. It just means that the force that is causing the acceleration does not change. But what I want you to do is I want you to take a minute and I want you to sketch a possible graph that could represent a variable force, or a force that is changing over time and is changing as this object moves from one point to another. I'll give you about 5 seconds. Now, your answer could look very different from mine, but a variable force is just going to be a force that changes over time. Maybe you did something that was a zigzag. Maybe you did something really simple and you just did a nice straight linear line, but the force was increasing over time. Maybe you did something a little bit more dramatic, like maybe there was a curve involved. Regardless, when we're dealing with a graph of a variable force, we're really just looking at a force that is changing as time goes by. But again, same as the graph on the left-hand side of things, there's a slope and there's an area here that we have to be concerned with. Now, in the interest of full disclosure, the slope of this graph, think about how we calculate slope. It would be rise over run, or the force divided by the distance. And so if we want to make a note of the fact that the slope of this graph here, or either one of these graphs, would be our change in force divided by our change in our displacement, you are certainly welcome to do so. However, whatever number you would get, whatever physical quantity you would get by taking a change in force and dividing it by a change in displacement, is not going to be a useful quantity, not something that's going to give us information about how our object is behaving. Rather, what I want us to focus on is a concept that we saw before when we talked about velocity versus time graphs. And that is this idea of the area under the curve, the area that is bound between the line of the force and the x-axis of your graph. And if we look very simply here, just at the graph on the left-hand side, we're going to deal with a constant force here for a second. If I go over here and I look at the area, well, that shape here is a rectangle. The The area given by a rectangle is base times height. So here that's going to be the force applied times the distance. Now, let's make a very general assumption here that the force we're concerned with was applied to an object that moved a certain distance in the same line of motion of that force. That would make the angle between these two 0 degrees. And the cosine of 0 degrees is 1, meaning that if we assume that this constant force is acting in the same direction that the object is moving in, what that really means is that the area of a force versus distance graph or a force versus displacement graph is the work that is done by that force on that object. The same is true over here on the right-hand side of things. The area of this force versus distance graph is also the work that is done. But if you notice, based on the shape of that graph, this is a curved line. This is not something that we would be able to use our algebra-based physics skills to solve. This is something that would require an integral, which is a calculus skill that we are not focusing on in honors physics. However, what you might see is perhaps a force versus displacement graph that is a variable or a changing force, but one that instead of having a curved line is maybe something that has a linear change. That area, that would be something that we could still calculate the area of. It's a trapezoid. We could do a little bit of work with that. Wouldn't be anything too hard to deal with. So what I want you to make a note of in your notes, the most important takeaway from right now, is that the area under the curve, this area bound between the line of the force and the x-axis of a force versus distance graph, is the work done by that force on the object. Now, we're going to put a pin in that particular concept for right now, and we're going to come back to how we actually use that in problem solving here in a later video. So right now, all you need to know is that if you have a graph of the force acting on an object over a certain distance or displacement, then we can concern ourselves with the area under the curve because it will be equal to the work that is done.